Hi, I'm JB Baker, VP of Product Management and Marketing over at ScaleFlux. I'm going to give you a quick rundown on deploying SSDs with computational storage and the expectations versus what we're really seeing out in the world. Just background, we've been hearing a lot about computational storage for several years, but how is it really playing out? That's what we're going to talk about here. So first off, what were the expectations around computational storage, and what are we trying to achieve? Well, when we look at the definition that we have specified in SNIA for computational storage, we had some goals around alleviating bottlenecks, whether it's CPU bottlenecks, memory bottlenecks, or network bottlenecks, and enabling parallel computation. We were going to achieve that by reducing data movement and offloading host processing. So pushing some of the processing tasks out of the CPU and down into the storage devices or near the storage devices. And the expected benefits here were going to be improving application performance and improving the overall infrastructure efficiency, basically doing more with less, get more work done with less power, improve your TCO, improve the sustainability of your infrastructure. So all these sound great, but how are we doing against those in the real world? I'm going to run through a few examples of customers that have deployed computational storage drives, what benefits they saw, what challenges they did run into, and then we'll do a quick summary at the end. So first example here was Alibaba that's running a hybrid transactional and analytical processing database. It's an in-house database called PolarDB. They had challenges around network congestion and data processing hotspots and memory congestion, where trying to run analytical processes and transactional processes at the same time across shared storage with multiple compute nodes was causing tons of data movement. So we worked with them to develop a predicate filtering engine that sat in each one of the drives. So in the controller in the drive is a hardware engine to do that predicate filtering. Alibaba also had to do changes to their application in order to push the predicate filtering down into the drives and recognize that parts of the query were going to be handled down in the drive. So significant upfront effort to make this happen, but major benefits were achieved. They saw a 50% reduction in the PCIe traffic, just the raw data that had to leave the SSDs. They saw a 70% reduction in the network traffic, how much data had to move from the storage nodes to the compute nodes. And then up to a 10x performance improvement in the queries per second and processes per second that were being handled by the compute nodes. Second example here is an OLTP. This is a cloud service provider whose name is confidential, and they are running a MySQL application. What they saw was pain points in their infrastructure overall. The cost of delivering the SLA and the reliability around the MySQL deployment and the MySQL cluster were very high. So they tried out using our computational storage drives with transparent compression to see what that might be able to do for their systems. What they saw was that they could achieve the same SLA and the same, not just the same performance, but also the same reliability or better reliability for the overall cluster with half as many servers and a quarter as many drives. So this improved their TCO, and then by that reduction in component count, further increased the reliability of their cluster. The third example here is a streaming data capture. We have a financial services company that's capturing market data for high-frequency trading. They ran into significant problems with their current infrastructure with being able to have enough write bandwidth to capture all that data at the latencies that they require. And just with that high throughput of writes, it was also causing challenges around the endurance of the flash, where the flash could wear out in advance of the server replacement cycle. So again, trying CSDs with transparent compression for something very simple. What they saw was being able to store twice as much data per gigabyte of flash that they purchased, being able to increase the max fill rate of the drive. So instead of setting a max fill of, say, 70% in order to maintain the performance that they needed, they could bump that up to 90%. They saw an increase in the lifetime petabytes writes per gigabyte of flash that they purchased. So doing the compression reduced the write amplification, reduced the amount of data that was written to the flash per gigabyte of host data that was sent to the drives, and improved their overall latency. So very happy with the solution in total. All right, last one here. This customer has lots of different applications. They're an online payments and services company. They have several different databases that they use in their payment processing and fraud detection activities. So key pain points here, a little bit different depending upon the application. So with HBase, what they saw was that with the rate of data generation, they had a shrinking window between when they needed to offload from the SSDs out to archival storage. It had been months, and now it was days. And so being able to store more data locally in the flash was critical. For MySQL, the cost of scaling capacity to handle their ever-growing database. And then with Aerospike, trying to achieve the latency goals, particularly around fraud detection, for their rapidly growing transaction volume has become a pain point. So once again, we're trying computational storage drives with transparent compression to see what this can do for their infrastructure. And what they saw with HBase was now they could store more data per gigabyte of flash, and that allowed them to expand that backup window back out without increasing the cost of their system. For MySQL, again, storing more data per gigabyte of flash helped them reduce their cost to store all of the data. And then on Aerospike, with the improved latency profile, they could achieve their transactions per second goal per server, or get more transactions per second per server without increasing the cost of the system. So with all these examples in mind, how are we scoring against the goals, tactics, and benefits that we set out in the industry? Just using traditional report card method here, I give most of these an A minus. All the examples were definitely alleviating bottlenecks, whether CPU, memory, or network. Definitely enabling the parallel computation instead of choking the CPU with a task. We're distributing it across multiple devices. We are offloading that processing from the CPU, doing that compression directly in the drives, or the data filtering directly in the drives. You can see that we've improved application performance. Several examples here of reducing the cost of the system, getting more transactions per server, so improving that overall infrastructure efficiency. The one here that I put as a B is that reducing data movement. So in the PolarDB example, certainly we were reducing the data movement dramatically with that filtering that sat down in the drives. But in the other examples, we're not really reducing overall data movement. We're doing the distributed compute. So, I with that wonderful glowing report card, it's pretty clear that computational storage should be everywhere, but it's not. So what's the problem? Why isn't it being adopted everywhere around? Well, the report card doesn't cover every aspect that buyers are going to consider in choosing whether or not to deploy computational storage. There are some key things that are missing from that report card. As you can see on the slide here, there are real concerns and there are perceived concerns about the complexity of delivering that. And I'll go into a little more detail in just a second. There's standardization. So when we started into computational storage, there were not any standards around it. This is being addressed very well by SNIA and NVMe, with standards being published around computational storage, how to identify devices, how to program functions, and how to push those tasks out to the devices. Security has been one that came up as we started working through the standards and pushing compute tasks out to the drives and out to accelerator cards. Found that, those might open up holes in your security to enable more attack avenues. And so that those are also being addressed through the standards committees. And then there's aligning the ecosystem, where a computational storage device may be able to significantly help an application, but either it's got to do it automatically, or if or the application has to be modified in order to take full advantage of that computational storage device. And if the application vendor has to modify their code in order to take advantage of a hardware, well, they're not going to do it unless that's going to help them sell more software licenses. So we got to make sure that whoever's doing the work to enable the computational storage is also going to derive a benefit, or the incentives are aligned. And then for every one of these functions that we look at, whether it's us or another hardware vendor or a software vendor who's working on the computational storage devices, we got to feel like there's a big enough market to justify doing the development for that specific function. Now, regarding the complexity, again, some of these are perceptions and some are real complexity challenges. And this is a very simple, age-old type of analysis of cost versus benefit. So if we look at the expected benefits from deploying a computational storage device or function on the y-axis, and higher is better, versus the complexity of deploying that function, or how much do I have to invest up front to deploy it on the x-axis, and here higher is worse. So the further we go to the right, the harder it is. Functions where we get a lot of benefit for very little complexity or very little upfront cost, those are no-brainers, but that's also those are kind of the unicorns. And then, of course, if it's too complex and the benefits aren't very big, then a user's going to say, why are you bothering me? Please go away and don't call me again. We go a little bit lower on the benefits, but keep complexity low, or upfront effort to deploy this very low. And now this is where we're getting the most traction. So you saw in my examples, most of them were around the transparent compression, which very, very simple thing to deploy. So transparent compression or other transparent functions are going to keep that complexity low and enable you to get significant benefits without having to change your application or have specific skill sets, things that can be applied broadly across different industries and verticals. They may still require some changes in either application settings or management tool settings, or in how users buy their hardware. So, if you're typically buying servers pre-populated with whatever SSD the server vendor chose, that's a change in behavior to then go and select your SSD to get the advantage of computational storage. As we move up and to the right, we have kind of these two that are kind of interesting. And I think these two areas are where a lot of people went to in their heads when we started talking about computational storage. These big benefits of being able to do my custom functions right down in the device and really make it perfect. But these get to be more challenging because of the reality of the complexity around these. So either we have to allocate a bunch of resources up front and do development before we're going to start to realize the benefits, or there's joint development that's going on here. And if the perception is that the benefits are high enough versus the complexity, even there, the user is typically going to need more buy-in, right? They're going to have to escalate to their boss or pull in other functional teams to really assess whether the value is high enough and whether they have the resources available to deploy it. And then if they're not quite sure, if they like the idea, but it's too complex versus the benefits, then there's a deeper investigation that has to happen of, can we get more value from this, or can we reduce the cost and the upfront effort to deploy the computational storage? So in both of those situations, now that return on investment calculation or TCO calculation starts to get more complex, and there's a lot more knobs to turn, and it just takes longer for people to get over the hump on that. So that's where I see key challenges for computational storage becoming ubiquitous, is this that perceived complexity, the real complexity, and then us as vendors of computational storage devices helping users solve those. So to wrap it up, computational storage has started to deliver on the promises that we set out with. The standardization efforts are significantly helping in that and will make things even easier going forward. But we still have challenges, and that's why it's not ubiquitous. Users may not have the skill sets to develop or deploy those customized functions, or even if they do, they just may not have the resources to allocate to putting that effort in upfront before they start to realize benefits. And then also, as we start deploying computational storage and more functions, we start to peel the onion and identify additional challenges and additional benefits, challenges to security and potentially additional benefits in the TCO. So that's the scoop. Happy to have you guys reach out and ask me additional questions afterwards.